Uh, okay. So, can you see the screen? Fine. Is it clear? Just wanted to make sure. Okay, so I just want to thank the organizers for giving me an opportunity. It's always nice to come back virtually, at least, to and give a talk. I'm a little bit nervous, but it's still good. Thank you for this opportunity. So I will say I graduated in 2015, so I was a student of MS 10 batch. I worked with Krishnendu for my master's thesis on hyperbolic geometry. And then I started my PhD at George Mason University in 2016. And as I was saying, I am planning to graduate this year in 2022. So that's about me. And so today I want to talk about dynamics of group action on varieties. So this is a little broader idea of my research topic. And my advisor is Professor Sean Lawton at George Mason University. And I I've structured the talk in such a way that I haven't added too many technical details because it might be harder to put so much information into 1 hour. So my goal is to kind of give a broad idea of what I'm working on and give a flavor of the research area or the topic I'm working on, which is a small area of algebraic geometry. So I hope I'll be able to accomplish that. And so I have defined some of my definitions are a little bit not too concrete and less technical, but I mean it to give a, like I said, give an idea of the. I've been aiming to give an idea of the concept or the topic rather than too technical. So if you're really interested in any of the topics and if you want more definitions, you can always let me know. I can give you references or explain it in more detail after or email any other way. Okay, so when I talk about my research, I kind of think of it having 3 components. So the first and the major part is my dissertation research, which is in algebraic geometry. And in this part, I have been working on understanding so I work with these objects called character varieties, and I look at a group action on these varieties, and I try to understand the dynamics of this group action. So that's the crust of what I'm doing. But then another project that I worked on and is still working on is I try to understand some applications of varieties in data learning. So I don't know if I will have time, but maybe if I have time, I'll briefly explain like what I mean by that. But if I don't have time, what I try to do is we take data sets and we try to understand, can we approximate it to some varieties? So similar to what they do in manifold learning, so trying to approximate data sets to manifold. So there is some interest recently in using algebraic geometry for data learning, and it's a very slow process, and I've been trying to work on it because I'm not very familiar with coding. So, but it has been an interesting counterpart to my dissertation research. And the third one is math education. So I'm interested, I like working on, I like teaching. So I kind of like to try and learn more things about improving my teaching and in general in mathematics education. So at George Mason, I was able to participate as part of 2 projects separately. One was an undergraduate project it was called Improving Undergraduate STEM Education. And the goal of that one was to actually implement something called inquiry-based learning in calculus classes. So what we do there is try to help the students discover math rather than just teaching them. So kind of making it a little bit more based on learning and less on memorizing. So, and then another another project that I worked on was for graduate students. So that's where the department started an initiative to help the students improve problem-solving skills by running active learning problem-solving sessions. So I was able to be part of that as in the algebra courses. So these were both projects with a team of faculty members and students. So that's something I was interested in, so I just wanted to mention this. But most of my talk will be focused on my dissertation research, which is algebraic geometry. But if you have questions or if you're interested in anything that I'm saying, like feel free to reach out to me if after the talk or even email anytime. I would be happy to answer what I know. Okay. So the structure of the talk is, so I want to start out with a definition of varieties. And I want to, and like I mentioned before, I think I'll give a loose definition to kind of have a working understanding required for the talk. And if you want, like, because going into more the technical details of defining formally would take much more time. And then I define what are character varieties, and specifically, like, what are they? What are these objects, and why do we care about these character varieties? And then I move on to like these varieties. I'm interested in specifically the finite field points of these varieties. Okay, and then like I mentioned before, the main focus is this group action. I'm looking at this group action on character varieties, and I want to understand the dynamics of this group action. It's called arithmetic because I'm working over finite fields, so it's a arithmetic dynamics rather than a topological dynamics. Okay, so that's the structure of the talk. Okay, so varieties are probably most of you know the definition of varieties, but if you already know it, please bear with me. I just want to give a rough definition of varieties. So you can think of varieties as a simultaneous zero sets of a collection of polynomials. So for example, think of a unit circle. So if you have a circle, it's a set of points x, y such that x squared plus y squared equals to 1, right? So you can think of, if you look at this polynomial, x squared plus y squared minus 1, then you can think of a circle as zero set of this polynomial, right? So circle, so in that sense, circle is a variety. And so when I say circle, you're imagining it, the shape circle, right? Which means you're placing it in some affine space, right? You're looking at it in R2, the real numbers. So in general, when you define varieties, what we do is we have a field K. For example, in the circle we had real numbers. So we take a field and we look at the sum affine n space, which means n tuples of that space of that field over that field, and then you put some structure on it, and we want to put some topology on it, and it's called Zariski topology. So what we do there is we take all zero sets of collection of polynomials, and we say that, okay, those are going to be the closed sets of the topology. Okay, and that's called Zariski topology. And once we have that, if you want to, and now what I'm saying now is more a formal definition. So if you want to just ignore that, feel free to, and just think of this definition. Okay, varieties are simultaneous zero sets of collection of polynomials. That's good enough to have some understanding. So like I said, we take for a more formal definition, take the affine space, and we put this topology on that space, and then we say that, okay, now we take any irreducible open set there, and that is going to be that's an affine algebraic variety. Okay, this is a very basic way of defining. Now you can generalize this to generalize this even further, but I'm not going to get into any of that today. So now what I want to say is, okay, so what is algebraic geometry is about is, like as the name suggests, we want to use algebra to understand the geometry, right? So that is the main idea of algebraic geometry. So if you look at this, coming back to our example of the circle. So if you look at this example, f of x equals x squared plus y squared minus 1, then what is the circle? The circle is the set of points where the polynomial is 0, right? So if we want to attach an algebraic object, we kind of want, what would be a natural way to do that? So since we have already a polynomial associated with this, and if we look at the polynomial ring, and in the geometric shape, this polynomial is already 0, right? So if you look at the collection of polynomials or the polynomial rings, then we also want the polynomial to be 0. And how do we make polynomials a 0 in a polynomial ring? We quotient it out by the, whenever we want to make things 0 in groups or rings, we quotient it out by those, right? So we take the polynomial, we take the quotient of that polynomial ring by, so in general, if we have a variety V, which is the 0 set of these f polynomials f1 to fk, what we can do is we can associate a ring. So we take the polynomial ring in n variables over this field k, and we take the quotient by the ideal generated by these polynomials. And this ring is called coordinate ring. And that is a basic idea of algebraic geometry, that we have these basic objects called variety, which are the fundamental objects that we study in algebraic geometry, and we associate these algebraic objects called ring. And this allows us to use algebraic tools to understand, because now we have this rich field of commutative algebra and a lot of toolbox coming from there, which we could use to understand the geometric structure. So this is a very general, and like I said, this is very broad way of, I'm not giving a lot of specific details. If you're interested, you can refer to a book like Hartshorne, or there are even introductory level books which would be easier to access if you're interested in that. Okay, so now I want to define character varieties. So this is like the name suggests, they are of course varieties. So they are 0 sets of some polynomials, and so to define character varieties, they have 2 components. One is a topological ingredient, which I call gamma, and the other one is a geometrical ingredient, let's call it G. Okay. So the topological ingredient gamma is a finitely presented group. And it's a group, right? So where does the topological component comes from? So this gamma is, you can think of it as a fundamental group of a surface. Again, I put surface in quotes because like it varies what you mean by that, depending on the type of gamma. You can have, so at least any finitely presented group can be represented. It doesn't always have to be manifold. It could be the fundamental group of at least a CW complex. So, but we work with specific examples of specific surfaces that different people work with different types of surfaces that they are interested in. But so this gamma captures the topology of the surface, and we take that, and now what do we have? Then we have this group G, and it is an algebraic group. And an algebraic group means it has 2 structures. It's a group structure, it is a group on its own, but it also has a variety structure on it, which means it is a 0 set of some polynomials, and it has a Zariski topology and all that. And these 2, of course, when we have different operations, we want them to be nice and compatible with each other. So we have these nice properties as well. And for this discussion, I want to work with some nicer, I want to work in a nicer setting where I'm working over complex variety, and I want to have something called reductive groups. So complex, so I want to work with complex reductive groups. So reductive means, it's a little bit more technical. What it means is the unipotent variable is trivial. It's the it's one way of the traditional way of thinking about it. Another way is you can think you can take a compact Lie group and you can take it is a real algebraic group. Then you can take the complex zeros of these polynomials and any affine variety that arises as this complex zeros is actually a complex reductive group. But if you don't want to think of all of this, you can just think of it as like, think of this group SL and C. That's good enough. It's a set of all matrices, n by n matrices with complex entries in determinant 1. So it is a group, it is a variety, and like I said, these complex reductive groups usually come from a Lie group. So this also has a Lie group. This is also a Lie group, which means it has a manifold structure. So these are like so many good and nice structures that we can use. Okay, so so now we have these two components, right? We have the gamma and we have the G. Okay, so now what we do is, now we can define the character varieties. So the fundamental set of this, or the fundamental objects in this character variety, we start from the homomorphisms from gamma to G. Homomorphisms are always interesting, right? Because their representations are like, it helps us embed things into some other structure and use that structure also, right? So we take this home set, homomorphisms from gamma to G, and then, so I said this gamma is finitely generated, right? Which means, sorry, I meant finitely presented. So which means, what I mean is that it has finite number of generators, say R, and it has a finite number of relations. So if it has finitely many generators, then I can take the image. So for any homomorphism row, I can like just find the image of the generators, and that will be sitting inside GR, right? So through that evaluation map, I can have this, and this map is always injected. So I can have the homomorphism sit inside this R copies of G or group G, and this map is surjective if I start out with the Lie group with no relations on it. And this is nice now, because then that gives, so this homes, initially it was just a set, right? But now, since it is embedded in the GR, we can think it gets some variety structure. So it gets this topology and the variety structure and all these nice structures from GR, which, okay. So now, now what we do is, now a lot of times when we study these representations of homomorphisms, we are interested in their equivalence up to conjugation, right? Because one reason could be that, like when I mentioned earlier, this gamma comes from the fundamental group of the surface, right? And when we compute the fundamental group, it is coming from we have a natural choice of a base point there, which is not a natural choice, right? Because we can have different base points. So, but choosing a different base point corresponds to conjugation. So, which means having these type of equivalence classes help us help us have these things independent of the presentation that we choose in the beginning. Okay, so what I'm trying to say is it's good to have up to conjugation, because a lot of times we only care about the properties that are independent of the conjugation. Okay, so you can think of it as two ways. We take equivalence classes of these homomorphisms up to conjugation, or we look at the orbits of this G act on this home set by conjugation, because it's sitting inside GR. And so we take these orbits, and this is what these are the objects that we care about, okay? Because we want to study this. But the problem is, whenever we want to study with something topology, we want it to be somewhat analytically nice. And this space is not very nice. We cannot analyze the space because it's not even T1. So it's not very friendly to analysis. So what we can do is we can kind of make it nicer, right? I mean, we can kind of approximate it to something nice. So we throw out the bad points. So we say, okay, what are the points that are not nice? So we approximate it to these points where we take the closed orbit. So we don't consider, we take the points here that, that give rise to closed orbits. And this subspace of closed orbits is what we call character variety. So this is the symbol for character variety. So this is the G character variety of gamma. And so if it's too complicated of a definition, so you can think of it as like equivalence classes of homomorphism. So another way, it's the same idea, but another way to think of it as it is equivalence class of homomorphisms, and two equivalence classes are two homomorphisms are same if their conjugation orbits. So whenever the equivalence relation is whenever their conjugation orbit intersect, then you consider them the same. So that's one definition. So you can think of it as equivalence classes of homomorphisms or up to conjugation. And since I'm working in this nice setting, there is another point of view that you can, if anybody is interested to think of, that is the definition I work more with. So this is also the geometric invariant theory quotient of, which is actually, and what you do there is, okay, I don't want to go into that, but that is another point of view that might be interesting. And that's what that definition is what I usually use more, but I feel like this definition is a little bit more intuitive and motivating to see why we study character varieties in some sense. So there are different point of view to look at these objects. So that's what I wanted to say. Okay, so let me give an example. Okay, so we start out with a surface of, which is a one-hole torus. So when I say one-hole torus, I mean like the regular torus with a puncture in it, with a hole. So then the fundamental group of the surface is generated by these two, this red loop, which is gamma 1, and the blue one, which is gamma 2, and they don't commute. So it's the free group of rank 2. So it's finitely generated, it's free, which means it has no relations on it, okay? So now, let's look at this SL2C, it's the 2x2, so our G is going to be SL2C, the 2x2 matrices with entries from complex entries and determinant 1. Then this is a popular theorem by Foucault, which says that in this case, this is actually going to be isomorphic to C3, which is just the affine 3 space. And if anybody is interested, this isomorphism is actually given by the trace of gamma 1, gamma 2, and the product gamma 1, gamma 2. So that gives the isomorphism. There is actually a paper by William Goldman, which uses very elementary, he has an exposition of these results using very elementary techniques. So if anybody is interested in reading that, I can provide a reference. Okay, so so this gives so in this example, so now it has like you have something to imagine, right? So the character variety in this case is just the affine space, okay, like the whole space. And another, okay, I want to introduce one more concept. So once I have this character variety, we can do one more thing. What we can do is, we always go back to the surface in time. So I look at the surface and it has a boundary component right here. So I say, okay, I want to fix the values that this boundary component can map to. So like we look at this loop of the boundary component in gamma, and I say that, okay, I want to put this additional condition that this boundary component is going to map to a fixed value, say this C in G. Okay, so so what I mean by that is, so how do I translate this? So when we calculate this boundary component, it is actually the commutator of these gamma 1, gamma 2, and if we actually like calculate this polynomial x squared plus y squared plus z squared minus xyz minus 2. This actually defines the boundary value, and I want to fix that to a particular value equal to c, and this is called the relative character variety, because now we are putting an additional, fixing the boundary components, right? And when there are multiple boundary components, you can have multiple values for each boundary, different values for each boundary component. That gives a relative character variety. Okay, so okay, well and good. So all is good so far. So, but one of the issues here is like, this is complex numbers, right? And it's harder to visualize complex numbers, but this is, we are defining this over this one field, complex, right? C, complex numbers. But we can also, once we have the structure of the variety, one thing we can do is we can also look at how does this look over other fields? For example, like circle, like I mentioned, right, earlier. Circle, I have real numbers, right? So, I mean, when I said circle, we always think of the shape circle, and which means we are thinking of it like we are making the choice, we are looking at the field real numbers, right? But you can also look at the circle over rational, right? Like what are the rational points of that circle, or you can look at it over integers. Won't be much interesting, but you can, right? Because so you can do the same thing. So if instead of looking at these points, once you have the structure of the character variety, you can look at it over different fields. There is one condition you have to be careful. So for example, if I want to look at the real points of this variety, so this will be just r cubed, right? Because instead of c cubed, it will be r cubed. But when I look at the relative character variety, in order for it to make sense, I want to have these coefficients of the polynomials should be equal, should be real numbers, right? If it is something, if I have a complex coefficient here, then I cannot really make sense of that over real. So this is another reason I work with complex reductive cases, like the condition I added earlier, because there's a theorem which tells me, because I mentioned in the beginning, I'm interested in what I am interested in looking at finite field points, right? What I mean by that is like, so if you look at this polynomial again, I'm calling it kappa. See, you can see it has integer coefficient even, not just real, it is integer, which means you can also look at what are the integer solutions of this, right? And when you look at the integers, if you know, like if you can calculate the integer points, then you can also calculate like z modulus z mod 5 or z mod 10 or any ZP points. And you can even look at the finite field points. So that's even possible for these ones. So this is where I want to go. And that's why I work with also the specific category of reductive complex groups, because it allows me that it gives that the varieties, the polynomials defining the varieties will be usually defined over integers, or at most maybe 1/2, but that is fixable. We can, if I avoid working with even characteristic prime field, then that is fine. Okay, so this is an example, right? So how does this variety look like? So if we see here, so this example, see this is the character variety that I told you, like that the relative character variety for a specific value of c and over real numbers. Okay, so I want to show one more thing. Let me quickly share something else. Okay, so I want to show, so it's okay. So I want to show this. So if you look at, so this is the variety that I showed for the one value of k. And if I change the value of k, so this is, so for each k, we get a different relative character variety. So you can see how it changes, right? See, it changes. So this is even changing the topological structure. See the connected components, this is not even connected, but as we increase, this is connected. So I just wanted to show that like the different character varieties have even different topological properties, even though it is from the same character variety. Okay, just something nice. And I also have this 3D printed character variety. This is this one for some value of kappa, fixed value. So just want to show that. Okay, so back to our talk. Okay, so these are all, and this is all, I usually do my calculations using Mathematica. Okay, so this is the real points, right? Now, how does it look over finite fields? So I mentioned I have the finite field. That's what I'm interested in, right? So if I want to look at the finite field, so you see the green is the real points, and if you look at the red dots, these are the finite field points of the same varieties, the related character variety. And this is for a fixed prime. I think it is 5 or 7. I think these are the points over Z5, Z mod 5 or Z mod 7. I don't remember exactly. It was a while back, but one of those. So smaller primes, because it's harder to calculate. It takes a longer time to calculate these things when you go up in numbers. Okay. So now I hope I gave some idea of these, what character varieties are. So I want to give some motivation of why do we care about character varieties? Why is it important? What is useful about this, right? So like I said earlier, so this is this gamma, the finitely presented group, it encodes the topology of the surface, right? And this G encodes the geometry. And so once we fix this group G, and so it has a fixed geometry, it has a type of geometry, and gamma has a type of, it has a fixed topology, right? And we are trying to see in how many ways can we have these different type of geometries imposed on this gamma, right? So that's what we are trying to understand, and this helps us learn more about, have a better understanding about the geometric and the topological structures on these objects, right? So that is the main reason why these objects are interesting. Yes, so same way like the by representation theory is interesting. It helps us to understand structure of groups by and groups can be thought of symmetry, right? It helps us to understand the symmetry by using topology, right? So that's the main motivation, and where it comes up natural. So where this is like used, it comes up naturally in mathematical physics, for example. So Higgs bundle is something that comes up in string theory, that character varieties are very closely connected to Higgs bundle. So a lot of people, mathematicians who study, or a lot of people who study character varieties are actually mathematical physicists, and the not invariant theory, people who study not invariant theory care about character varieties because they look at this not complement as character varieties of not complements. And one other reason which I personally like about this is it brings together different areas like number theory, algebraic topology, mathematical physics, differential topology, algebraic geometry, all of these areas a lot. And we can, so it has this rich, these are very rich objects in the sense that they bring in, you can use these tools from like number theory or some even combinatorics, and it allows you to look at different, see the same object from different perspectives. For example, like I have talked to physicists who study character varieties, and they have a totally different view of character varieties. And even my research, when I explain, they look at it from a different point of view. Number theory see it from a different point of view. I see it from a different point of view. And people who study topology and interested in topological dynamics look at it from differently. So and that increases and deepens the understanding of the subject, as well as like allowing, so it is at the intersection of these like different areas, which are nice. Okay, so a little bit of history, just how this name came about. I think it came from, arose from this work by Peter Shallon and Mark Kohler in 1980. They published a paper, Varieties of Group Representations and Splittings of Three Manifolds in Annals of Mathematics. And one of the theorems they proved was actually the space of SL2C characters was a variety. So I mentioned when I talked about the Fricke-Wood theorem was the isomorphism. It's given by the trace functions, right? The trace functions are characters, and this is actually, so it's a variety formed by characters. So I guess that's how the name comes from, character variety from this paper. So, okay. So now talking about the group action. So so what I'm interested in is I take these character varieties, I look at their finite field points, and I look at action of outer automorphism group of gamma on this character variety. So let's, what is this action? It's basically, so we have the home set, homomorphisms from gamma to G. We can look at the action of automorphism group of gamma on this, right? We can just pre-compose, because aught gamma is going to send any element in gamma to gamma itself, and then you just send it to G. And I have this inverse here because so that it's an action, and that's fine because it's rho is an automorphism, so it is going to be inverse is also an automorphism. But since automorphism group acts on home set of gamma, what happens is outer automorphism group is quotienting out by inner automorphisms, and inner automorphisms are through conjugations, right? So this naturally act on these character varieties, which is also a conjugation orbit or closed conjugation orbit. So there is a natural action of this out automorphism, which is basically arising from these points, from this action here. Okay, and this is interesting because a lot of times these actions helps us to understand the structure. So sometimes these character varieties could be harder to understand. So actions on character varieties help us better understand these objects sometimes. For example, like this is a very simple example and just an analogy. So like that circle, if I give you a circle, and if you don't know it is a circle, if I don't tell you it's a circle, you have to figure out, like one way you can do is like, you can just like, you can try to rotate it, you can try to reflect it, you can see what is happening when you do these actions to the circle. And depending on, like, for example, like a circle, if you rotate, nothing happens. But if you have a square, rectangle, if you rotate, its shape, it changes, right, to the structure of the that it is sitting in. So just a very simple example. So what I'm trying to say, so you can get some idea about the geometry or the structure of these objects by looking at studying actions on these objects. So, and a lot of times, so for example, when gamma is free, outer automorphism group of gamma is something called mapping class group. And mapping class group basically means it's a set of diffeomorphisms, a special class of diffeomorphisms of this surface surface that we start out with. So, and that is very interesting. That action is interesting because it helps you understand the topological properties sometimes. So that is why people traditionally study this. They started, I'll explain it a bit more here. So people started studying, actually, Dr. Goldman, I think, was one of the people who initially started maybe 1997, some of the these studies on this. Okay. So before I explain that, let me see what I mean by dynamics. So I said studying action, right? What do I mean by studying the action? So I want to see, so what we are doing is we have these points, right, on varieties, and by doing this action, we are moving those points around within that variety, right? So we want to understand this motion. So how is this happening? So how can we make sense of these things? So some common things to study, or something I particularly study, I'm interested in, is one is transitivity. So can any point go to any other point through the action? Okay, and another property, another aspect that you can look at is the orbit. What is the orbit structure? So orbit means it's kind of tells you the range of motion of a single point, like where can one point go within that variety under the specific action. And so what are the different orbit structure, or what is the size of orbits, or what is the biggest orbit? So we can ask questions like these if you're trying to understand dynamics. And one other property that in this specific case, a lot of people are interested in is something called ergodicity. And what we mean by ergodicity is, okay, suppose like I mentioned transitivity, right? Excuse me, which means any point can go to any other point in the variety. But if that is not possible, what is the next good thing? Is like, okay, can we do something like other points going to almost every other point in the variety? What do I mean by that? It means it is missing only like really small set and like a very small number of points in the variety. And how do I quantify that really small? And so if you have a measure defined on the space, you can say, okay, it's missing a point, a really small set of measure 0. And that's what ergodicity means. So it means like the action is transitive almost everywhere except on a set of measure 0. And so this question, Dr. Goldman, I think conjectured that for compact Lie groups, it will be this action of mapping class group on character varieties will be ergodic. And in 1997, William Goldsman and Picker and Sham, they showed that the action is ergodic for if gamma is a closed surface group of genus 2. So if you're considering the closed surface of genus 2, their surface group, then it is going to be ergodic. And then furthermore, there were more. So since then, there has been more interest, more people have been studying these mapping class group actions and ergodicity and the other properties like properly discontinuous action and other aspects of this. But this is the traditional version that people study. What I have tried to do is I look at this character varieties or finite field, and I try to understand the dynamics of that, right? So there is not much there is not much research done on this, because people who try to look at this action, they are coming from a topological point of view. And when you look at finite field points, you don't really get any topological structure, right? So they are not that interested in that. But I like working on this because I look at it from a number theory point of view in some sense. So it gives it brings in some more number theory, and it gives a different perspective on the on some of the solutions. So like when we are trying to look at the action, it helps to solve some like there is an interplay between number theory problems and these ones. So I kind of like the number theory aspect. And another thing is when you're looking at it from a topological point of view, what happens is like, so you have a shape, right? Because you have this continuous set of points. So what happens is, so what happens is you get mostly distracted by these shapes and not distracted, that you care about these things more. But when you look at finite field, like it allows you to look at a little bit more on the finer structure of the character variety itself, because you just have a collection of points. So like you look at these points and kind of like look at what is happening in, like, for example, like you can do stratification and look at what is happening in strata and things like that. So it's a little bit different perspective, and I kind of like that. So that is another reason I work more on this aspect. Okay, so but the problem when I work with finite field is there is no measure theory idea to measure. There is no natural invariant measure, geometric measure to kind of make sense of this ergodicity, right? So then what we can do is, so we introduce, me and my advisor, we kind of introduce this notion of asymptotic transitivity. So what I mean by that is, see, I want to see, okay, like this same idea, right? What do we mean by ergodic? Like there is a big orbit, and that orbit is almost as big as as the whole space, right? So what I can do is, since my set is dependent on this prime Q, right? So I'm working over finite fields FQ. So what I can do is I can take the limit. So my size of my set is of my variety, or the collection of finite field points dependent on the finite field Q. So I can look at the asymptotic case when Q goes to infinity. And then I take the ratio of, okay, what is the biggest orbit ratio and versus the size of the variety? And is this ratio going to 1? Which kind of tells you that it's almost as big, right? And okay, so that is one way that I try to make sense of ergodicity in a finite field setting. Okay. Example, not of transitivity, arithmetic asymptotic transitivity, but just these are the finite field points, right? I just wanted to show like how this is the same points. If I look at the action of outer automorphism group of F2, free group of rank 2, not the whole group, because that's an infinite group. This is just the action of a single element, and you can see, I just want to show like how excuse me, how it gives the how the orbits look like in this example. Okay, because this is something we've been looking at. And yeah, this visualization we did as part of a project we did at the experimental geometry lab along with undergraduate. So this one is not just my work, we did it together. And okay, so my approach is for my research, what I do is I did 3 things. One is I looked for transitivity. Is this action transitive? And another thing, if not, can I find a big orbit, or like big is like really, like can I find a like transitive orbit, or some kind of like something that gives me some insight into the structure of the orbit within this character variety. And then finally, I want to check for asymptotic transitivity. If the action is asymptotically transitive. Okay, and want to give a very simple example. So if you look at the abelian, so instead of free group of rank 2, look at the abelian group, the free abelian group of rank 2, which is C2, and look at the action of this automorphism group of Z2 on home Z2 SL2 FQ. And then automorphism group of C2 is GL2C, which means a set of 2x2 matrices with integer entries, all invertible matrices. And if a matrix is invertible in Z, that means the determinant has to be invertible, right? In integers, which is +or -1. So these are basically matrices with determinant +or -1 with integer entries. Okay, so if you remember what I said earlier, we can have this home set sit inside 2 copies of the SL2FQ, right? And but this is not a free group. We have a relation, right? Because this is a abelian relation. The generators commute with each other. So we need to make sure that we can only choose points here. So the image of this home set will be the set of tuples in 2 tuples in SL2FQ that will commute with each other, right? So that's all we need. And this action is not transitive, as I can show you here. This is for a very small case when I choose so I wanted to give it, so because I feel like a lot of times it's very abstract. So just to give a feeling of how it looks like, when we take Q equal to 2, which is the smallest prime possible. So then this is what we get. These are there are 5 different orbits. And like I mentioned earlier, I got this by looking at just the generators of Z2, because it's hard to do it's an infinite group, so it's not possible to do like the iteration for all of the elements. But we can actually prove that this is going to be all the orbits. Like there is no more, you cannot go from any other orbit using any other element. So this is actually all the orbits in the home set. But this is the home set, right? All of these points don't go to the character variety because not all has closed orbit. So actually the ones I have like squared, see this one, this is the identity element. This is, that is all usually by itself. And this one, this and these. So these 4 points are elements of character variety. Each of these will be closed orbit, but this won't be closed. Yeah, so this will not be a closed orbit. So this won't be there in the character variety. So this is one example. And if we go one further, if you look at F3, the Q equal to 3, then it's like even bigger. And this is the case for the action of generators on only the generators. But it's also possible to show that this is not transitive. So this action is also in general not transitive, even though that cannot be concluded from the picture. This is just to show how it looks like. Okay. So just a little bit background on asymptotic transitivity, which I mentioned. So we kind of coined together this term and this concept is not, there is not, traditionally there is not much, it's not popular in the literature, but recently there have been more interest in this topic in this area. So these Bourgain, Gombard, and Sarnak, so they have studied the solutions of this kappa, the kappa that I mentioned before. So this is slightly different than the kappa, but because it has a coefficient 3, but this is the same type of, and they also worked on a similar case, same kappa. But they are number theory. So these are number theorists, and they are interested in this because this equation is something called like a Markov type equation. So this gives a Markov surface. So they are interested in the interested in it from a number theory point of view. And they don't use the term asymptotic transitivity, but they work very specifically in this for this, and they call it something called a strong approximation conjecture, and they actually prove that is true, which actually is equivalent to asymptotic transitivity. So that's some literature on this asymptotic transitivity. Okay, so now just to summarize what I did with respect to work is, so one of the results is I showed that for most groups gamma and G, the action is not transitive on the finite field points. And there is like a very special type. And if it has to be transitive, it has to be a very special type of G. And for special type, then I define these groups called groups of free type. And that by that, I actually mean I want to have groups which has automorphism groups similar to that of free groups. So like it allows permutation and inverting the coordinates and left and right multiplications. And if that is the case, then the set of epimorphisms within the homomorphisms form a transitive orbit under this action. So that's the other thing. So that is kind of like the big orbit. And I think, so I need to do more calculations on that to figure out how big that is in the finite field case. And outer automorphism, then the out gamma action is not asymptotically transitive on SL2 and SL3 free abelian character variety. So it's not asymptotically transitive, and we also like give a bound for, okay, this is going to be the maximum size for the orbit, like so we give an upper bound for the size of max orbits for this action on these SL2 and SL3 character varieties. So this is like the main general idea of what I did. I think that's probably a good point to stop because it's 7:28. Sorry, yeah, it's close to the ending time because but I kind of want to, yeah, okay, so yeah, this is the data learning stuff, but I guess I don't have much time. But I kind of want to like mention end on this note that they're like these are peripheral things to mathematics research, but like these are some things I'm interested in, and I have like been associated in small capacity. So if anybody's interested in talking about these things, I'm happy to talk about it at any time. So like experimental geometry lab or association for women in mathematics, and student-run seminars, math outreach activities, active learning, or inquiry-based learning. Just wanted to have it out there. But, yeah, so thank you for listening. Guess I'll stop now. Any questions?
Thank you very much for the nice talk.
Thanks for the nice talk.
Questions, comments?
Thanks, Cigole, for the nice talk. Yeah.
Thank you.
Yes, so Kapil, would you like to ask something? Or yeah. Okay, Cigole, I have a question here. Yeah, sorry, so Kapil, you go ahead. Yeah, then I will ask. No problem.
Go ahead. Go ahead.
No. You can ask, and then I will ask. It's all right. Yeah. Please.
Everyone is saying you first. Okay. You know, there are specific varieties for which you know the fundamental group, and then these give varieties of representations give rise to modular varieties of things and so on. Have you looked at those questions? Like, for example, the finitely generated group can be the group of a Riemann surface.
Yes. Yeah, so I think it.
One. Yeah.
Mm-hmm.
Have you looked at some of the other cases, kind of? And
yeah. So no, I haven't looked at that one, but I think like that there is like whole. So yes, you were absolutely right. So these are like. So these character varieties are more like spaces, right? Because we're questioning out with something. So a lot of these, exactly, like so a lot of these cases are like interest, like a lot of the interest is coming from like spaces like Teichmuller space and like Riemann surfaces and these things, and like a lot different people have studied. Like there is a whole. I think that is what a lot of people study, and that's more popular, and like a lot of interest in this field because of that.
But you are looking at it for number theory.
Little bit. Yeah, I'm a little bit more from the number theory, coming from that perspective. So I haven't looked at that aspect that much.
Fine. Okay.
Yeah, so I was asking a similar question, like when gamma is a free group. When gamma is a free group of generators. I mean, what sort of action outer Fn has on the character variety of SL3? Yeah, so so when gamma is free, we have one nice thing that the homomorphism set is in bijection with the R copies of G. So it's nice, but other than that, I think the action is the same as, so the action is the same. Yes, okay, so for free group, yes, okay, so actually I have, that was one of the applications. So when gamma is free, this action is almost never transitive, because the action is transitive if and only if we have like if G is a cyclic group of prime order. So that is the only way for that, which is a very restrictive case. So that is the only case we can get transitivity in the free group case, and when gamma is free. And for the free type, like the result I mentioned. So I'm talking about that from my point of view, from what I have studied at the moment, is the epimorphisms. The free type group is also a free group is also a free group of free types. So that gives the set of epimorphisms again form a transitive orbit. And the free group character variety include. I have looked more at the free abelian character variety for the symptotic transitivity case, because that I'm starting to build up, and there is not many tools and techniques to understand that. So that I'm starting from like the free abelian case. So I haven't. My next step is I want to look at the free group action on SLN character varieties first. I think because SLN character varieties are nicer to start out with. Before going to general cases, I think, but because some of these problems are the problem. The one of the disadvantages using number theory is sometimes it's like even small, easier problems, like even with simpler primes, it could get really hard. Like one of the things when we were working on this was like we often end up with, sometimes we would end up with like, okay, if this is equal to Riemann's hypothesis. If we just have the Riemann hypothesis true, then it is going to be fine. Like this also we can prove. So like, which means like we often come across these roadblocks, which is even for simpler cases. So yeah, I don't know, does that answer the question, or were you looking for
Yeah. It's all right. Yeah. Fine. Perfect. Yeah. Thank you for the nice talk.
other questions?
Any other questions from the audience? Questions, comments? I guess not. So then let us thank the speaker once again. Okay.
Thanks, Cigole. Yeah, thank you.
So Cigole, thank you
Thank
very
you.
much.
Thank you.
Thank you very much.
Nice
It
to
was
see
really,
you. Yeah.
it was really good to see everyone. Thank you. I really feel like I have given some talks, but this is like, it's more exciting because I don't know, I feel more like I really like, it's good. I have a lot of good memories with IISER, and when I think of it's really nice to be back. So thank you.
Yeah. But you should be back actually to visit us, Krishna. Will tell you.
Yeah, hopefully. And I also want to say for the students, if you have like any questions or like anything, feel free to ask. If I know, I would be happy to answer. I probably don't know. Yeah, so like, but if I can help, I would be happy to help. So.
Yeah, wonderful.
So next time when you come to India, just keep us posted.
Yeah, sure. Yeah, I don't know when that would be, but yeah, I would very much like to visit.
Yeah. Okay. Bye-bye.
Okay.
Bye.
Take care.
Have a good evening. Bye.
Yeah.
See you later.